My name is Jay Schmidt. I work at MindWare, and I'm going to be presenting this study for you today on analyzing ECG data. Specifically, we're looking at a stress induction task, and we'll be showing you how to analyze that. Okay, so just to get started, before we actually start looking at the MindWare HRV application and looking at the ECG data, I'd want to describe this experiment that we're going to be covering today, and then it'll make a little bit more sense when we're looking at the data. So the first thing that we're going to occur in this study is we're going to look at a baseline. So, we're going to bring the participants in, consent forms, all of those things that we're used to, sort of let them habituate to the area a little bit, see the equipment kind of settle down a little bit, then we're going to go ahead and start our baseline. So typically this is done simply by having them sit quietly. Some baselines are reading something very low cognitive workload so they can kind of just relax and get down to a normal state. Simply just coming into the lab can induce a little bit of stress in some people. So, getting all that done even before the baseline is helpful as well. But in this case, we did a 3-minute baseline. We really collected ECG, and really, to talk about why we're doing these things, the baseline will really let us get that sort of that starting point for everybody. And what is their basal high frequency heart rate variability? What do we see before we even try to induce any stress condition? This is helpful so that, when we're actually looking at these tasks and conditions that induce the stress, or that we, are hypothesizing or inducing stress, we're, able to actually offset the difference between participants. We can see their baseline information, we can compare that to the condition. And then that enables us, by having that offset, to really compare, across different participants. So for a between subject analysis. And so the baseline is very important in these senses. And in a lot of studies, we'll actually see that there's multiple baselines. So if it's going to be a longer study, or if you want them to be able to recover, you could simply call that a recovery stage or another baseline. Another really important thing to do for those of you that might be doing the Trier experiments, the TSST is a social stress test. A common sort of entity of that is that we're actually going to ask them to stand to give a speech. And so if we're looking at certain metrics, such as impedance cardiography or anything to do with blood pressure, we certainly want to know when those postural shifts change and when they actually stand up. And so having a sort of note about that, another baseline, perhaps, a standing baseline would help us a lot, because we don't want to use sort of the sitting baseline and then use that for a standing portion to offset. So multiple baselines are definitely welcome. And again, that could also be a recovery. After we get the baseline, though, in this case, we're going to induce this breathing task. So what we can imagine here is that the question is, what effect does meditative breathing have on our ECG? Is the meditation really necessary, or is it just the effect of the breathing that helps us control and relax, if you will? And so what we'll do is we're actually going to ask half the participants to conduct that meditative breathing for about 6 minutes. And then the other half is going to be the control. So they're not going to receive that meditative breathing. They'll simply do something else. Again, some sort of low cognitive workload, in this case, a reading task. And then we'll actually induce the last condition, which is the cold pressor, or the real stress induction entity of this. And so in this case, these participants are going to place their arm into a bucket of icy water. In a lot of instances, it's sort of hold it in there as long as you can, and then remove it. In this case, we're going to ask them to do it for at least 180 seconds, or 3 minutes. So the idea here is that we can see if this breathing task has the effect and is able to provide those protective features for that person once they're inducing the stress induction. So that's the cold pressor. So if we have the breathing, the meditation actually works, do we see a reduction in the actual stress response once they place their arm into the bucket of icy water? So that's the general idea here. That's what we're trying to do. We're trying to be able to compare across participants in most cases. Naturally, there are some studies in which we're going to try to just do within subject, maybe a longitudinal study, and where we're doing repeated visits. And we may not have to do some of these steps. But in this case, if we did want to do that sort of between the subject analysis, we do want to get that baseline, and then really see how everyone recovers and see if that sort of hypothesis is correct. So I'm going to go ahead and exit this now, and we're going to jump right into the MindWare HRV application. So when I go through this, I'm going to be referencing some support articles, some online features that everyone can access at any time. It's free. There's no login. And near the end, I'm gonna represent and show you exactly what that looks like. So if you're a little bit confused on where to find the information I'm calling out, don't worry about it. I will definitely cover that in the end. In addition to that, just due to the time limitations of the study and the scope of it, we're not going to go through every single setting here and how to sort events and things like that. We're really going to focus on the actual data and how do we clean it. We do have plans in the near future to provide a sort of comprehensive what should every setting be. But as I'll also cover later, we do provide complimentary one-on-one consultations. So that might also be a better use to sort of get the exact answers for your specific study and your specific research questions. Going through, we're really going to focus on time mode with the data. I will show you, very quickly how to open a file. It's pretty straightforward. We're going to load our data file, and then here is where it's going to ask us to map the channels. So in most cases, if we labeled this correctly and we required the data, we're just looking across and selecting the correct title. In this case, we are going to talk about respiration quite a bit. And in this study, some other measures were also collected that we will cover in future webinars. And one of those is impedance cardiography. So basically, that's where we're actually going to induce a little bit of current through the chest, and we're going to see sort of that change in conductance of the blood. And then in that way, we're actually able to non-invasively track blood flow. One of the additional benefits of impedance is that we can also derive respiration. Respiration is, in some regards, going to be very important when we're validating some of the high frequency heart rate variability metrics, such as RSA or RMSSD even. And so we definitely want to ensure that in most cases, we collect respiration along with the ECG data. That's usually very critical. If this is not done, there can be a lot of questions that you can't really answer, and then you'll basically be funneled into having respiration as a covariate. So if we can easily apply a respiration belt, or if we're just happen to be also collecting the sympathetic side of things, such as impedance, we just get this bonus of deriving the respiration from there. So by mapping it in this way, obviously we'll want our ECG, but if we also map these impedance channels, the application will know to derive the respiration from those. If we did have a respiration belt, sort of the traditional approach, we could unmap these, make them white, and then we would turn on our respiration channel. And I'll show you exactly when we do map it in this sense. If we actually go to the calibration settings, you'll see here under the respiration signal, it does know to automatically use the Z0 or Z0 as the respiration. So we're all set there. Okay, going back to the events and modes real quickly, I just want to highlight that, again, we're not going to have any events in here. We're not sorting by sort of events that occurred during the session. Those events can come from keyboard presses, of specific instances in the study, such as the beginning of baseline, the end of baseline. Those don't have to be their own files. Those could just be event markers that we're placing within one file. So there's multiple ways to kind of break this down and look at the data. But in this case, I'm doing this without events to kind of keep things simple. Again, we will be doing an events and modes webinar in the near future. And then if you have any additional questions with that, that'll certainly clear it up. So one thing to note when we're doing this time mode is in most cases, we're going to want to, in almost all, we're going to want to standardize the amount of condition time between participants. This doesn't always need to be down to the millisecond, but it certainly can help if we can standardize it in some way so we're not comparing 30 minutes of data to 20 minutes of data. We don't want that much of a sort of shift in the amount of data that we're comparing between the subjects, but certainly a few seconds is okay in most cases. If you're certainly not comfortable with that, there's a very easy way to standardize that in these cases is just to uncheck that file end or file start, whatever 300 seconds in this case that we wanted, because again, this is that baseline information. So we could simply pick, baseline being 180 seconds. We can choose any 180 seconds within here. So I'm going to go ahead and just choose the first 3 minutes. So we can type that in. And then as soon as we go in, actually do the analysis, we'll see that we only have the 3 minutes and we're going to automatically exclude the rest of the information. Okay, so before we do get started, though, I do want to go back to the calibration settings and just speak about the importance of this page and when we should visit that. So really, from the default settings, most of this is fine to, as is. One thing I would recommend that you pay special attention to is the high frequency RSA band. So this is our normal recommended settings of 0.12 to 0.4 hertz. This is the frequency at which, after we pass the ECG data through a fast Fourier transform, where we expect the RSA information or the high frequency heart rate variability information to lie. This is in adults in a normal resting state. So if we were looking at a different population, certainly a different species, we would want to change these settings. So a very common one would be, children, neonates, infants, all of that sort of group. They're going to have a much higher heart rate. They're going to breathe faster. And so we need to compensate for that faster frequency. So in most cases, we'll change this to something about 0.2 all the way up to about 1 hertz. There are articles, again, that I will show you near the end of this that will show you exactly where to find that information, scientific literature that surrounds it, and then provide some recommendations based upon your current population. And even if we were doing adults and these settings were okay, we still have to consider their sort of conditional state. Are they resting? Are they sleeping? Are they exercising? Are they on a treadmill? All of these different things could influence how fast they're going to breathe and may influence these changes here. Okay, so now is a really good time for me to go ahead and actually start editing the ECG data that we have for our baseline condition. And so I'm going to hit Analyze. Okay, so I'm going to briefly describe all of the different windows, these different little portals that we have, how we use them to inform our edits, and how we also use them to validate the information to make sure that it's good integrity. So the first window we have here, as you can see with the title, is the actual ECG plot. Nothing too fancy here, except that what we've done is our algorithms have gone through and they've tried to identify the peak, some sort of singular fluidicial marker on every beat that we can then use to compare to the next beat. So for instance, what we really want out of this is not, in most terms, the amplitude. That's not of concern to us in this case. We're not clinically diagnosing any sort of condition or treating some illness. We're simply looking for the timing between the beats. We want to see the sort of vagus nerve effects on the heart. We want to see how it's modifying the heart rate, and we want to look at the frequency between those. So, certainly when we see something of a different amplitude, that's noteworthy. We're always going to zoom in. We're always going to make sure that we for sure have the correct peak identified. But it's really not the end all. We don't need everything to be flat, and in most cases it won't be. What we really care in the end is about the timing between the blue dots, or the interbeat interval, the timing between the beats. So this second chart shows us just that. It's really taken the timing and then plotted it on this chart for us to look at. There's usually not a ton that we inform ourselves about from this chart. It really is showing us the process, but in some cases it certainly can help us correct something that we may have missed. So for instance, when we're looking at this data and we see these very sharp points of inflection, that's something that, even if everything looks blue and that's the algorithm telling you that it's likely good data, we probably don't have to make an edit. This still would grab my attention that there is a lot more variability here than we see for the rest of this file. And there's certainly a shift here. This is certainly just the timing slowing down. We can even visually see that the beats right here are a little bit shorter in time in between them. And then all of a sudden this slows down. And we'll talk about that in just a second, why that's happening. But that's noteworthy for sure. So both of these locations would be great areas to zoom in and pay special attention to. After we have this timing, we're going to interpolate, we're going to detrend the data, and we're going to build this heart period time series graph. So it's going to be very highly correlated to the IBI series. It's really just a way in which we're going to smooth the information out before we pass it through the fast Fourier transform. You want to do this so that we're not introducing this sort of artificial timing and noise, such as these really sharp peaks. We really need it to look like this. After we do that, we're going to taper the data, which is basically in essence, taking the beginning and end of this heart period time series, and if you will, imagine wrapping it around and connecting it to itself. Because one of the postulates of the fast Fourier transform is that we have a continuous signal. It can't be a periodic one that begins and ends. It just doesn't function. So what we need to do is bring those points together and taper them so that we're really minimize the amount of information that's removed or added. So once we have the heart period time series information, then again it's submitted to the FFT, the fast Fourier transform. And then if we look on the right here, we are now presented with the heart rate power spectrum. So now if you look at the Y and the X, we don't have time involved here at all. Simply the amplitude, which is reported in milliseconds squared on the Y, and then on the X we have the actual frequency going from 0 all the way up to the right. And this is really where we get most of the information about the high frequency heart rate variability. And so from this point here, which is 0.12, we just saw that before, and I was drawing everyone's attention to it. That's that one section where we need to make sure that our population is kind of in that condition. So 0.12 all the way up to 0.4 hertz. And so I'll go back really quickly just to show everyone this is how we would actually change the location of those vertical bars and tell the application this is the area that you need to pay attention to. And so that is represented here as the 0.12 to 0.4. There is a yellow bar directly behind this white one. It's hidden because if you've noticed, the low frequency and high frequency both share a band of information. We don't want any missing frequencies between them. But in essence, if we went from this to this is really where we're gathering all of the RSA information, in addition to all the other high frequency heart rate variability metrics we have. And you can see those over here in the time domain area. And again, if for some reason we didn't want to use RSA, we wanted to use a different metric of high frequency heart rate variability, RMSSD is usually our second choice. Okay, so now we can see how the information is passed through. These other bins that you may be noticing here, they may have less significance to you, but this lower one here, this is the very low frequency. And both of these lower sections are comprised of both sympathetic and parasympathetic effects. So basically from 0 all the way up to about 0.12 in resting state adults, and we don't know how much of each. So the sympathetic nervous system, the parasympathetic nervous system, they can both influence heart rate at these lower frequencies. However, at about 0.12, again, depending on the condition of your population, from about 0.12 up to about 0.4 or higher is just purely parasympathetic. So it's just an effect of the sympathetic nervous system not being able to work that fast, and the parasympathetic one is much faster. And so we know that any sort of resulting change in the heart rate is due to that vagal mediation, or the vagus nerve. The low frequency can also have some significance to you if there were specific research questions revolving around baroreceptor activity and blood flow. There is the Mayer wave, which can be analyzed in the low frequency spectrum, which you can find there. But predominantly what we're looking at is this high frequency spectrum. Finally on here, you'll see that there's a respiration time series. This is a lot easier to kind of comprehend. This is, so if we simply inhale, it's going to go up, and we exhale, it's going down. And we're showing it here just as sort of a validation procedure, because what we're going to do is we're going to take this time series data, and again, we're going to pass it through the fast Fourier transform, and that's going to result in this frequency spectrum, this power spectrum. And so one of the things to do is to ensure that what we're looking at is actual respiration data and not something else, not noise. And we want to make sure of that. So one of the things to do is we're going to look at the respiration rate and just very quickly visualize to see if that makes sense. And really we're talking about maybe plus or minus 5 respirations. And we're not going to go in and count. It's just a simple visualization to say, is this 60 or is this 6? How far off are we? And then 15 looks just fine. What we're really doing in the end, what we need to do and pay additional attention to is the peak frequency of respiration. So you can see that's up here in the top right. In this case, it's at 0.25. And so it's really picking likely this point right here. And what we want is we want that to be within the same band that we're reporting that high frequency heart rate variability. So if that's 0.12 to 0.4 hertz, we likely want to keep that respiration bands at exactly the same thing, because the goal in the end is to use the respiration data to ensure that they're breathing within normal bands. And once we can do that, then we're really validating that RSA or RMSSD metric. So the respiration and the importance of it likely ends there for most researchers that use MindWare. But there are certainly those that have specific questions that revolve around respiration itself. So in those cases, we could certainly look a little bit closer. But in this case, for this specific study and what we're talking about today, we really just need to make sure that we have good quality respiration time series data that results in a peak frequency between these two bands. And that's all we really need. Okay, so now that we have an idea of these different windows, we certainly have the statistics over here, which are maybe a little bit more self-explanatory with the titles. But just to go over them briefly, we do have the heart rate. I've talked about respiration rate and peak frequencies, the mean heart rate or the average heart rate within here, mean interbeat interval, so that is the mean average amount of time between the beats, and then simply just count the number of beats within this segment. From here, these other statistics are likely not going to be used too much, but individually, if you were interested in these things, we will give you the power in each of these spectrums, the peak within there. And then here is the sort of all-important statistic that most people are using MindWare's HRV application for, which is RSA. And lastly, we do have some new features in the 3.2 application that I'll highlight just briefly. This is one of them, and it certainly is a big time-saving feature. What it is editing statistics. So we have a couple of rules. There's about 3 or 4 that I'm going to give you today that are really, suggestions, scientifically founded suggestions on how to edit this ECG data. If there are artifacts or if there is ectopic abnormal physiology, how do we edit that data? And so one of the rules is known as a 5% rule, and or can also be expanded to a 10% rule. And really what that's saying is if we ever had messy data in which we couldn't see the actual signal through the noise, it was too noisy, maybe this one we'll investigate here at around 3 seconds qualifies for that, we're going to estimate where that beat occurred, because what we're trying to do is have a continuous signal. Remember, we don't want to interrupt that without a beat. If one didn't exist, in most cases, we're going to place it there so that the fast Fourier transform has this continuous signal. And that really leads us into the second rule or recommendation, which is 30 seconds. And this is pretty ubiquitous throughout most of the literature with looking at human ECG data, is that in most cases, we have a minimum of about 30 seconds of uninterrupted continuous data. Most groups will expand this up to a 60-second interval, which is what we're doing here, if you look at the time series, because then we have a lot more freedom in how we edit the data. Let's say that this information we see at 3 seconds is too messy. We really don't want to estimate where the beats are. Then what we could do is we could simply start at 4 seconds, use all the information up to 60, and we still have way more than 30 seconds, and we've collected a lot more of that high-frequency data. So there are different strategies to use that, but in essence, we want to stay below 5 or 10% of the estimated beats. We need to have at least 30 seconds of data, ideally 60. And then, the other thing is a mid-beating procedure that we'll go into in just a second. So what I'm going to do now is I'm going to go ahead and hit the Edit Rs button. Again, we're not going to have time to go through every single setting here. I will show you some online resources, videos that will go through this for you to look at. But right now, I'm going to go ahead and open up the editor. We do that by hitting the green R, or the Edit Rs. And here we can see we have a lot of various settings. We're going to be focusing a lot really on the point editing and the mid-beat procedure today. And if we look at the bottom left here, we will see that I also have some tools available. This first one will let me grab either the X or Y cursors to move those around. I'll show you how we use those in just a second. The second one is a zooming window with these icons. You can see the varying different abilities here. This top middle one is sort of my favorite to use in HRV because it'll keep the 1-axis constant. So I can always see the amplitude of the ECG data, and you'll see why that's important. So I really fluctuate between this one and then zooming all the way back out to the entire window, which is what we see right now. So let me go ahead and use this first one. I like to initially look at about 10 seconds of data. And it certainly depends on the heart rate and the population that we're looking at, but usually 10 seconds of information is good to look at it once. So I'm gonna go ahead and do that. Click and drag. From here, what I'm looking for are some fundamental components of an ECG QRS complex. And so I'm gonna go over those really briefly with you. So if we focus really on this cycle right here, this second one, I'm gonna go ahead and show the entirety of it here. So the first thing that we're looking for is known as the P wave. That's that atrial depolarization of the atria of the heart. And so we see this upward inflection. And that's really, the signal is, this sinoatrial node is sending out this electrical command for the heart, and these different blips, either up or down, are those electrical vectors as they go through the heart, the chambers of the heart. So really those atria depolarizing is what we see, this P wave here. And we really want to see that in almost all beats. It's not a mandatory part of the QRS waveform, but it certainly can help us when the data are messy to confirm that it's there, or in instances in which we suspect that this person may have some ectopic, which just means not normal physiology, or some ectopic beats. So again, it is very helpful in some cases, and when we can't see it, that's where we lean a little bit towards mid-beating or estimating where those beats occurred. But when we can see it, it really helps us verify that it's a good beat. In addition to that, what you will need is a QRS complex. So the actual points are this next little drop here is Q. R will be your peak. That is our primary interest in this situation, because in a lead-to configuration, that's basically where we put one sensor on the right clavicle, one sensor on the lower left rib. The R peak is the most pronounced and precise point. In theory, though, or really in practice, we can pick any point on the ECG waveform and compare it to that same point on the next complex. So we're simply picking the R peak because in this case, in a lead-to configuration, it looks like this, and it's really easy to see where that beat occurred and compare it to the next beat and continue on. Anyways, the QRS point in this situation, and because of lead configuration, is very necessary. So we see those points there. And then after the S, we have another blip. So this is going to be the T wave, and that is that ventricular repolarization. So the ventricle is the heart repolarizing. And once again, we're going to, in those cases, see that little kind of upwards mountain-looking blip there. So if we can see all of these components, the P wave, Q, R, S, and then a T wave, then that's a good beat. So as we move through the data, I have some messy data here that is actually going to be helpful for us to edit. And so we can see structures within this noise, which is likely a motion artifact. So they tugged on the lead, they touched the sensor, they stood up, something occurred in which the actual surface electrode was moving against the skin and caused a brief interruption in the signal, or what appears to be. And if we look closely, especially to a trained eye, we can see the actual QRS complexes. Maybe the P and the T wave are distorted because of the movement, but we can usually still see that actual QRS complex, and that's what we're after. So there's different varying degrees of sort of learning to edit the data, teaching other people how to edit the data, and then keeping everyone's edits consistent, so that inter-rater reliability. And you'll likely want to run that sort of intra-class correlation coefficient once it's all said and done, especially if we have multiple raters. So if with all of those things considered, you may edit the data differently, more aggressive or less aggressive, to keep things consistent between raters. So for instance, in this case here, what appears to be, just by looking at the general structure and looking at thousands of ECGs, this one appears to be an actual beat right here. But this is difficult. This is not something that you could easily give somebody across, a couple of students that might be rating this data and ensure that they're all going to pick the same point every time. And so one of the things we can do, there's a couple strategies. One is to set up the timing of some known good beats that occur prior to and after the motion artifact. So I can actually grab these X cursors, place them about, it doesn't have to be perfect, but about over the R peaks of this IBI that preceded it. I can then click this hand tool, which is really a click and drag hand marquee tool, keeping that timing constant and giving me some additional information on when that beat may occur. I can move this through the data and get pretty good ideas on which are the actual beats. And I can even attack it from both angles. If I knew, let's say I'd probably have to go all the way over here, I can reset my timing to see, to give me an estimate of when that may occur. Again, this is not always helpful because in this exact case, actually, we have two things that could qualify as an ECGB, and it's going to be almost impossible to tease those apart. So in this case, I think I'm quite certain that we're going to remove this artifact here, and we're going to place this beat where we can see it occurred, because we have these structures that do not look like the artifacts around them. Just even given the sharpness and breadth of the signal, this looks quite a bit different than the artifacts you see here. So we're likely moving through and causing that artifact here. And in this case, we could certainly pick the second one, but we are really getting into a guessing game of which is the actual peak, and we want to stay away from that. It may not have a huge effect in the RSA. It may, but it's also certainly going to cause issues within multiple raters. So to keep that consistency, or even sort of consistency within yourself, it's usually best not make any sort of assumptions here. So when we see that information, we're just not sure which is the beat, knowing that we have the 5 or 10% of the total data that we're allowed to estimate, this is simply a good instance in which we want to do that. What we'll do is we'll actually grab the X cursors, place them on the outsides, anywhere in this interval would work, but really on the outside of that beat, on that R peak. So same deal anywhere here, but we'll just throw it right there. If we do that, what you'll notice is that that application will tell you how many beats should have occurred within these two. So it's really looking, it's going to focus on this window and then how many beats should have occurred there. It's determining that based upon the surrounding average IBIs for this segment. And so if we actually place them on the outside here, it says you've missed one beat. We had a pretty good idea that was going to happen, and we'll hit midbeat. This will actually place a beat at, in this case, the mathematical middle between these 2 points. So what we're trying to do once again is we're trying to continue the data series, the ECG series, with minimal data added or removed to the FFT. And so by doing this, what we're actually doing is we're introducing 2 interbeat intervals in which there is 0 variance. And that would be a very proper edit to do. We certainly don't want to delete this and move it up to some random amplitude to try to pretend that we know that's there. Again, the amplitude is not the most important thing here. It's the time between beats, which is held constant here, whether it's at 0 or up higher. An additional thing you do not want to do is get yourself into the sort of confirming biases here. So if we were to place a point here and the MindWare midbeat application tells you it's there, and then you move the X cursor and you're like, I knew it was that one. We really don't want to get into that as well, just for consistency's sake. If we weren't sure about it in the beginning, we shouldn't be sure about it at the end after it places that point there. So we really want to leave it there. And if you notice, if you look at the bottom right, we've now gone from 100% of our beats being good down to 98.7, which is certainly within acceptable range. But we have estimated 1 beat, which only constitutes 1.3%. So you can see that you can do this quite a bit, whether you're holding to the 5% or to the 10% rule. And lastly, we'll see these pop up in just a second here, but this yellow is artifacts. So we haven't seen any of those yet, but as soon as we look at some messier data during the breathing and cold pressure task, we will see those artifacts occur. And so now I'm going to go ahead and I'm going to use the right and left directional arrow buttons. As you can see, I'm doing that to go through the segments 1 second at a time. It's a really good standardized way to see the same amount of information on the screen, keep that window constant, but move through the data in that zoomed in window. We can also click and drag the cursor up here. Both will work, but I just sort of like the 1 click means a second kind of protocol here. And so what we're looking for is we're really looking for beats in which we see, a yellow circle at the top, if you will. That's in us the simplest way to break that down. And then the rest of the segment looks pretty good. So we first come in, we ensure that our peak respiration frequency was within our bands. and then we will edit the data. Again, if this peak frequency does not, if it is outside, if it is higher or lower, then we likely want to not edit the segment anyway. So let's not waste our time trying to edit the ECG if we know that we can't validate it. Okay, so I think the rest of this is clean. So I just wanted to show you that baseline. And then we'll go ahead and open the different files. Again, this is the same participant, but just different conditions within there. Most studies will organize this into one file that, again, has these event markers within there. But in this case, we have separate sessions. Okay, so we're going to jump right back into this. Again, this is a 6-minute condition, so we can choose really, whatever 360 seconds we wanted within there. But let's just go ahead and the first ones. Okay, so once again, I'm not going to zoom in all the way. I would recommend that even if the data looks clean, we hit the edit Rs very rapidly, come in and look at the first 10 seconds, and just cycle through the data at whatever frequency you're comfortable with. But we're really just trying to make sure that those blue circles are on actual R peaks and not on noise. So we're done, and then we'll move through. Oops, sorry, still looking pretty clean. So this is a good example as well. We would certainly want to zoom in and see what that that was. If you have a video of the actual acquisition, that can help out quite a bit. In this case, it just looks like probably a motion artifact would be my guess, but this looks like that P wave was distorted. Again, it's not a mandatory sort of feature of qualifying that beat as being good. So what we do have is the QRS complex, the most important fundamental thing we need. And then it looks like we do have a T wave there as well. So this beat I'm actually going to leave alone. It looks like it was a sort of a shift. And then we have some messy data here that we'll certainly want to look at. When I'm doing this, again, I'm sort of moving a little fast here, apologize, but we do want to keep our eyes on that respiration peak frequency. Again, if that were sort of outside of those bands, our normal recommendation is that you do not use it. So just a quick check to make sure that's there, to make sure our respiration time series is making sense, and then we'll head at the edit Rs. Okay, and once again, I always like to, even though there's this really fun-looking artifacts that we can sort of clean up there in a little bit, we don't want to just jump to that section. We want to always start from the beginning and get to that point, because we don't want to sort of miss something that's in the beginning because of this other, again, very exciting artifacts that we get to clean. So in this case, it's almost like we have everything we need if we look through it. So we have the P, QRS, T here. This is a good beat. And then once again, you'll get really used to seeing this. It looks like there was a motion artifact. So because of this motion artifact, the beat really wasn't being detected. We can hit the insert beats. It will come up this circle. We place the maxima, the R peak, within that circle, and then it will automatically place it there for us. So pretty simple procedure there. If the software actually ever makes a mistake on that because of usually motion artifact. And then again, once again, I'm just clicking the right and left arrows to move through the data to see if I have any more artifacts to clean. And I do. So once again, some motion artifact, it picked up on the sort of peak detector that we have implemented. It doesn't see a lot of difference between the structure of this and the structure of that. As you can see, they're very similar. So it's detected what is likely just a motion artifact as a beat, and we just simply need to hit delete, same procedure, and remove it. Okay, and then the rest of that looks good. All right, so there is our sort of middle condition of cleaning that information. I'm going to go ahead and continue to save my data here, as you normally would. And then we'll look at that last section really quickly here. Okay, so that alert that you all just saw was basically telling us, hey, this file is different than the last file. If you wanted to look the same amount of time, that doesn't exist here. So just sort of an alert. It also comes up if there are events in one file that aren't present in the next one. It's going to assume that you're just editing data for a study and everyone should have those events. And so it's a way in which we can let you know if one is missing. So once again, this is the 3-minute condition of the cold presser, and we have 191 seconds. So I'm going to pick the first 3 minutes. And we'll start looking at this data right away. One of note here is the peak frequencies. The respiration data looks different than it did before, right? And we would expect them to be breathing differently once they're kind of going under that pain, under that stress induction. So the respiration's not always going to look perfect, But it certainly is very informative to us that we are indeed capturing the majority of the respiration information within the power spectrum. We don't need all of it. We just need the tallest peak, the most common frequency to be within there, which is right here. So it's not always going to look perfect, but really what we're talking about is, again, the peak frequency. So let's hit the edit Rs, though, now that we know that that's good, and let's just look at these data. Okay, so right off the bat, it's picking off this beat as being extremely long between these two. And if you look closely, we can actually see what appears to be another QRS complex, a little sort of mini one that occurs here. And so really what's probably happened is this, one of many different kind of ectopic occurrences could occur. We really can't confirm them with the setup we have of a lead 2 configuration. You know, you would need really that sort of clinical 10 lead or 12 lead configuration that you might have. And you would be doing something completely different. So in these cases, we really can't confirm what it was that occurs, and it's not our job to do so. But certainly looks like some sort of ectopic physiology occurred here, or arrhythmia. So what we're going to do in this case is we're going to just stay away from it. We're going to delete the peak that preceded it because, again, what our goal is to provide at least a minimum of 30 seconds of continuous data. So if I had to remove some information from the beginning and the end, that's actually perfectly fine, as long as I can control and ensure that I have at least 30 seconds remaining. And if you look and move the X cursors, the delta is the time in between, and we can see I have 58 seconds, so I'm still okay. Now I'm going to zoom back in, and we'll just continue on, and then we'll kind of wrap up the ECG editing for today. So right here, this doesn't really look like a normal ECG to me. I mean, that certainly looks like a peak, which could be that. But it could also be this person expressing some sort of ectopic physiology once again. And we don't want to include that unless we're absolutely 100% sure that that's a good beat. So we're going to remove that, delete it. Once again, we're going to employ our midbeat procedure of finding 2 good QRS complexes and then midbeating there. Very quick for demonstration purposes before I finish, though, there is no limit to the amount of midbeats that you can do. So let's just go ahead and remove this data and say that it just didn't occur. Obviously, we would have some questions for why that happened. Maybe it got unplugged. But I do want to demonstrate to you that we can actually, get a much more breadth of a sort of artifact and still deal with it by moving it to the other beats. It's still estimating I missed 3, which actually checks out from what we know, and it places them in those 0 variance intervals. This is actually the third and final recommendation that we have, is that you do not midbeat more than 3 times in a row. We're really starting to miss out on entire respiratory cycles, as you can see, by estimating these, and we really don't want to either inflate or underestimate RSA. So what we want to do here is keep this to a minimum of 3. It will let you go higher if you feel free to do so, but our recommendation is, again, no more than 3. Okay, so that is really, what if we continue on here, we're going to have more of these motion artifacts, removing this information, and I'll go ahead and show you this one last artifact, but in essence, that is fundamentally what we're trying to do here. And so once again, we can see we have a motion artifact here. This is a sort of distorted T wave. And really, this one doesn't look too bad. I mean, we don't see any similar structures that can confuse us or confound which one is the actual beat. So really what we need to do is remove that one artifact. So sometimes it looks a little daunting and it ends up being pretty simple. Okay, so that's going to go ahead and wrap up the active presentation portion of this. And right before we get started with the Q&A, I have a real quick presentation to show everyone, and then we'll get started with the questions. So I'm going to go ahead and do that now. Okay, so I'm just going to talk really quickly about our data analysis service, remote data collection, and training and support. Data analysis service is actually what we're talking about right now. We actually have a professional team that is able to clean your data for you. So if maybe this webinar was too informative and you feel like this is just something you don't want to get into, as much as you like the software, you'd like someone else to go ahead and take this off your plate, we do have a team available to do so for you. And as you can see here, we have a lot of built-in efficiencies and flexibilities to make that an easy process for you. So if you were interested, you could certainly reach out to us. I have a little graphic here that'll show you sort of these different meetings that we go through to ensure that we really understand your data, how it's going to be cleaned, how you want it presented. and how you want everything from the edited data files down to the output to appear. These are just some of the common measures that we analyze data for: heart rate variability, electrodermal activity, as some of you may know as skin conductance, impedance cardiography, and then blood pressure variability. Also with remote data collection, with the acknowledgement of this pandemic that is still occurring, collecting data, bringing participants into the lab is still sometimes challenging depending on your recruitment. And so one option, if you have a mobile or if you don't, and you might be interested in getting one, this is an actual way in which we can collect data from participants safely during these times. And so you can see here we have these different configurations, whether we're including the ECG and skin conductance, but we can also put a respiration belt on there. And so we have a lot of different flexibility, and then we have a little finger clip here if we were interested in also collecting PPG or photoplasmography. We certainly can have the participants put these wet gel sensors on themselves, or if they have someone else at their home and you're going to Zoom with them and really show them how to do this. We can also collect that heart rate variability information via PPG. It has its limitations, which we'd be happy to talk to you guys about, but it is commonly used as a proxy for the ECG. And then we also have a field laboratory integration platform, which is a mouthful, and we usually say FLIP. What that is really sort of a lab in a box, if you will. We have all of the networking and cameras, audio, video, the wireless telemetry that would communicate with our mobile devices, all included in this case. And as you can see here, you can synchronize this with stimulus presentation. If you're doing E-prime or some sort of presenting a video to them, we would want to know at what stage they're in the video and then what the resulting physiology looked like at that time. And then lastly, we're going to talk about the support portal really quickly. I promised you guys sort of how to get to the information that we talked about today. So support.mindwaretech.com. You can also just Google MindWare support. We can download software from here, create support cases, all of these different things without logging in. It's very easy to access. And there's also the sort of one-on-one and training options and different events that MindWare may be hosting online or hopefully one day back in person. So the first thing, if we look at the training, this is where we can actually get all of that. If you wanted some help with either one-on-one advice, you wanted to attend a seminar, you want to attend future webinars, you want the one-on-one complimentary training, all of those links and information is found within that MindWare training section. The training events here, this is what we're doing right now. So this is a webinar, and if we wanted to sign up for future ones, we can access that right there. At the bottom of all of these pages on the bottom right, there is a sort of subscribe to our newsletter. If you wanted to click on that, you can actually get an email every time a new webinar is presented as well. And then if we were to click on the training events, so let's just say we clicked on that oval there, this is what you would see, and this is where you can kind of sign up. And so if we want to continue this series and hear more of my voice, then we'll be doing another one on April 1st. That's not a joke. We're actually going to do it. And we'll be analyzing impedance cardiography, which is ICG, and then blood pressure variability. And then we have training guides as well I want to highlight. So this is, if you wanted to you're starting out or you just want to get some information on your own, the training guides are a great place to start. We've coalesced a lot of the knowledge-based articles and blog posts into this linear logical training guide. And so we actually have 3 available right now. If you clicked on that link, you can see those. I'm going to click on just the HRV. And you can see here we have everything from introduction to how do I put sensors on participants, how do I use Biolab, the actual software MindWare has to collect the data, previous software webinars, very helpful articles that we think are fundamental to ensuring you collect and analyze the data correctly, and then obviously additional readings. Okay, so now is a good point for the sort of live Q&A portion, and we'll get started on that in just 1 second. Okay, so first one I have here is how do I write statistics out? How do I compare between tasks? So yeah, I might have moved over that a little bit quickly, so I will certainly open up the application again. So what we would normally do if once we were editing the data is we would, again, confirm respiration, complete our edits, making sure we're under the 5 or 10%, whatever you're following, and then we'll likely write this out right here to Excel. The newest versions of the MindWare analysis applications actually write out to the XLSX format, which you can see here. So you don't even need Excel installed on the computer anymore. You could simply write it out and then load it onto a computer that has that later on. But this will actually help you write out that data. And if we went to that location, we could certainly look at that Excel page. And then 1 second while I get my next question. Okay, so really the question is revolving around if you're collecting impedance data, does MindWare adjust that high frequency HRV and RMSSD values given respiration rate? So what we're going to do is we're really going to ensure, it's the responsibility of the research to know that we're breathing normally. Certainly, visualizing them during the experiment can ensure that they're not hypo or hyperventilating. But if we didn't need to adjust, if we knew that we expected the respiration rate to be outside of normal range because of the stress condition, we can certainly justify that by moving those bands around. So if we needed to do that, you're likely going to do both of these things in lockstep, which is change the high frequency band and the respiration bands at the same time, which is why we have this button here that says use whatever bands we set here for the respiration. Because again, what we're doing is we're taking these respiration ranges, getting that peak frequency, building the respiration rate, and then ensuring that it's within the normal accepted ranges. So 0.12 to 0.4, if we actually look at this, it's based off a 1 minute cycle. So if we multiply these specific frequencies and times 60, we actually get a rate. So we would actually get 7.2 to 24. They need to fall within 7.2 breaths and 24 breaths within a 1 minute period. What it will do is automatically scale that down if you're looking at 30 seconds or 60-second epochs. And then there's an additional sort of extension onto that as far as, would this justify not statistically controlling for respiration and analyses? This really relies on the reviewer of the journal that you're trying to write to, but in most cases that won't hold up. You can certainly use the RMSSD statistic more commonly without respiration. So if you collected ECG, you didn't have respiration data, you want to express that high frequency heart rate variability, RMSSD is likely our recommendation. With RSA, it's a lot more sort of difficult to get that published, if you will, without the respiration data. Okay, so basically we want to know about a comment on why do we need 30-second epochs. So there's some fundamental literature. It's a 1996 heart rate variability guidelines publication where all of this is derived from. And in that, we're basically looking at how many data points do we need for that fast Fourier transform to work. And normally that's around 30 seconds, and it also will allow us to get enough, sufficient amount of breaths during that time. So if we look at much smaller amount of time, such as 15 seconds, we're certainly not going to get up to those 24 respirations. And unless we're looking at somebody that's we expect to be breathing really rapidly, they're on a treadmill or they're an infant. There are certainly studies out there where I've seen RSA published with less than 30 seconds, but it's one of those kind of states. Okay, and then let's see here. This next question is, can you repeat the second choice if you're not using RSA? I think I've done it a couple times, but RMSSD would be that second option if you're not going to use that frequency statistic. 1 second here. Okay, so this next one is going to be for RMSSD, how do we analyze the numbers? Basically, is it a lower number? Means there's more parasympathetic control? And then in what situations would you actually use RSA and RMSSD? So RMSSD is easier to calculate. It's often produced by devices that calculate in real time or do not record the raw ECG data. But if you do have the raw ECG data and respiration, then RSA is more commonly used. And I can kind of explain this and why the importance of that is if we know that both the sympathetic and parasympathetic nervous system can control the heart rate in these lower frequency spectrums, they're not as usable or relevant to us. So if we're looking at RMSSD, that's simply the square root of the mean and successive differences between beats. So it's including all of the time between the beats, which is including all of this frequency spectrum information as well. Obviously, we're not reporting on the frequencies in that case. It's just simply amount of time, but it is including those sympathetic effects. So if we use RSA, we can tease apart those sympathetic effects on the heart rate and just get a pure metric of the parasympathetic nervous system, or the sort of vagus nerves regulation of the heart rate. So that's the real advantage of using RSA over RMSSD. RMSSD does hold up better to long acquisitions, so multiple hours. If you wanted to collect data for an entire day, it'll hold up to those artifacts a lot easier than will RSA. You don't have to be as specific on every single beat in some cases if we're looking at those very long recordings. And so it's just a little bit easier to get done in some of those cases. And oh, sorry, and the last part of that question, as far as the variance and how we would interpret RMSSD. So, certainly everything's to a point. And if the data, though, looks clean, what we would interpret that as higher RSA or higher RMSSD would be more parasympathetic control. So an increase in RSA, an increase in RMSSD, increase in vagal mediation. Okay, so does the peak frequency range change for resting state EKG for older adults? So not for older adults, if you're looking at sort of the geriatrics there, but what we will want to pay special attention to is just the sort of children and infants. They're going to have a statistically different heart rate and respiration rate than with adults. So again, in those cases where we're usually bumping that frequency higher to the right, something like 0.24 up to 1 hertz is commonly used for children. Okay. So next question is the midbeat placement calculated from the overall IBI of the segment file, or is it looking at the section in between the cursors? So what's really happening here is the location uses the beats between the cursors specifically. So the number of beats to be inserted is calculated from the overall segment. It's not just looking at the surrounding, it's looking at every single interval, and what is that average? Okay, so next question is, why does correcting for the motion artifacts count towards the percent edited? So really, if we couldn't confirm that it was a good beat, right? We zoom in and we don't see anything that looks similar to a good beat. So let's zoom in on this one, for instance. If we couldn't confirm, if we weren't supremely confident that this was the actual R peak, that's when we would midbeat. And that's when that counts towards that percentage. Now, if this is just a motion artifact, which it looks like it is, but we can still see that peak there, the QRS is intact and looks good, we could even use our relevant timing to ensure. I mean, in this case, there's nothing else that looks like that, but just to show you, I mean, there's multiple things we can do to get an idea of where that should be placed. If all of that fails, that's when we would implement that sort of midbeat procedure, because we're just not 100% sure which one it is. And those are the cases in which it would count towards the 10%. If we can see that there's just been an error made by the algorithm, for instance, that it's just placed a beat, in the wrong spot, and let me just get this correctly here. So there you go. Okay, let's just say it places it over here, or it placed it down here on the actual data. That's the instance in which we're like, no, okay, there was just an algorithmic error. I can actually see the ECG. I'm going to delete that, place it in, and then it will not count towards part of 10%. It's an actual beat that was just incorrectly identified there. And the midbeat, we have another question here to how do we midbeat? So I'm going to certainly show you that again. Find a good data set to do that on. Whoops. Okay, so let's look at this messy section here, and hopefully we can find a midbeat to place in here. Okay, so let's go ahead and, this one before, as I said, it was pretty clean after we actually looked at it, but I'll go ahead and remove some data. Just as if the electrode came off or there was an actual missed beat that didn't occur in that participant, then what we look at. So you can imagine this as noise or electrode fell off, again, anything. But just to exemplify the midbeat procedure. So once again, I want to see good beats as my anchors, P, Q, R, S, actually some T wave there. It's a little distorted, but everything else looks great. And then same deal here. It's a little bit smaller, likely due to the motion artifact, has nothing to do with anything else in most cases. But fundamentally, it looks like a good ECG beat. QRS complex. So we're going to place these X cursors on the outside, and the outside being these yellow markers in this case, because before we place the midbeat, it thinks that's a very long beat, and so it's placing them as artifacts. Once we do that, we can actually see the algorithm is automatically identifying how many beats should be within there, again, based on the overall average for that segment, and then placing them there. And we're running a little bit over on the time here, but I will spend just a few more minutes getting some of these questions answered, and then we'll wrap up. So if anybody wants to stay around to hopefully hear the question, then I'm going to get that answered. If I don't get to it, then we can we'll reach out and answer your question via email. Okay. Yeah, so the next question is, sometimes there is an R peak at the very end of a segment, and the question is, should I mark that or not? And I believe one of these files actually shows that, but I could be wrong here. Okay. Okay, so I think this will work. So if we zoom in here, we can actually see what this person's talking about is if we have one of these right here, about 180 seconds, what do we want to do with that? In this specific case, I'm actually going to look at more data so that I can see what happens after that. If we couldn't do that, then this becomes a little more challenging, because what we're likely going to see is part of the ECG here, and then we're going to see the other part right here. And I want to ensure basically that it is a good beat and something doesn't occur afterwards. So if we weren't able to see after 180 seconds, I probably would just stay right here. It's not usually going to be worth your time to go in and add one beat on the order that we have 76 other beats in this segment. But if we did want to, I'm all about the accuracy. We could certainly look in. Once we do that zooming procedure, you're going to see you're going to kind of get to the end of the window. So that's another really helpful reason to use that hand tool and click and drag through here. So in this case, we actually have what looks like a really good beat. We could use our timing X cursors, and we can just visually see it looks like the timing is correct. But what's happened here is this beat is incomplete, so the software is going to say that it's happening between these segments. And so in this case, it's not going to place the beat anywhere. And again, that's not usually enough information to really worry about. But if we did want to use this, well, what we can do is we can confirm that P wave, Q, R, and then it looks like it's dropping back down. And this is really fundamental to ensuring that we're getting the right point here, is that the signal does drop back down on the screen. If it's still rising, we really wouldn't know where that maxima lies. And so we wouldn't want to include it on this segment. In this case, it's falling back down. So as long as I go and probably first check on segment 4 to ensure that everything looks good on that side, we can go ahead and retain it. So here's that signal coming back down, and then there's our S point, and then again, we have a good T wave. And so that would have been a good edit. Again, probably not influencing the statistics in a manner that we would really care about, but in those cases, or if that happens frequently, you can certainly do that. Okay, and then I got some questions simply more about the hardware collecting these data. So for the mobile data, what do we sample that at? And so the MindWare Mobile is a 500 hertz device, so that means that it samples the data at 500 times per second. The wired unit that MindWare has, this sort of other thing, we call it the BioNex. That's the sort of desktop amplifier that you might have. That samples natively at usually every channel at about 1 kilohertz or 1,000 times per second. You can actually upsample the BioNex to above that if necessary. It usually doesn't result in any additional information. It's just larger data files. But yeah, those are some of the differences between the two. Is certainly the sampling rate is 500 for the mobile, 1,000 natively for the BioNex. Okay. Okay, so really, the next question is based upon the baseline correction, normalizing ECG measures. So yeah, typically what we would want to do is, we want to, get that baseline information, and you can basically subtract that difference of the conditional information from that to get their data to normalize that. But you certainly do want to do that if you're doing a between subject analysis, so we can get that sort of starting point for each individual person. And then what we're looking at is the change between that and the stress condition, or how they recover for it. Okay, next question that I want to look at here is the, is there ever a time in which you would leave the yellow dots in the data? So yes, there is. In some cases, what you're going to see is not random, but once in a while, you'll see a very long IBI. And there may be sort of a question on why that's being caused. And in most cases, it is actually RSA. So we want to leave that there. What we'll see here, and again, this would be better if I had a specific example to show you. But really what we want to do is when we see that yellow dot, and I'm going to go ahead and just put one in here for us. Okay, so let's just pretend that that was initially there. What likely could have been occurring is that it's sort of the arrhythmia, or that change in the IBI was driven from the respiration. So in most cases, what happens is when we, well, hopefully always, all the time, when we breathe in, our heart rate speeds up, and then when we breathe out, it slows down. So if we do that in a dramatic enough of a fashion, we can actually cause a very short or very long IBI depending on where in the cycle they are. So for instance, if we started a respiration inhalation here, over the next course of these seconds, we would expect these beats to speed up. So the timing between these would shorten. And then as they breathe out, there's gonna be a little bit of latency, but right around here, we'd expect these IBIs to lengthen. We could certainly get our X cursors and go in and prove this to ourselves. It's not happening in a very dramatic fashion here, but it is occurring. So if this this beat right here, if this interval is extremely long, this actually makes a lot of sense to me, because they were breathing out. Let's say that this respiration was 2 or 3 times its amplitude. Well, that might cause enough to result in one of those a changing in that pace. There's also things such as cardiac resetting or resetting of the rhythm. So, you know, there's plenty of brain systems that have the ability to reset sort of that natural rhythm that the heart has. So if we just pick one, like let's say the medulla, we can basically send a signal down and speed up or slow down that sinoatrial node on how fast it's firing. So both of those things can occur. And what you'll see is that a sort of change in that IBI series afterwards. And in most cases, you're just going to leave that alone, because this actually psychologically relevant to what's going on here. And so the RSA information is normally left just as it is. The only thing to be really careful about when doing that, especially when you have multiple raters, is once we see this, we do need to go in and really zoom in and make sure that it is a good beat. So having the P and T waves is extremely helpful in that case. And if we're not supremely confident about it, even if we see the ECG data here, it's going to be safer and more statistically accurate to just mid-beat those out. So even if we were concerned about this artifact here, we certainly don't have to remove the information. We can just remove the beats, and we could mid-beat those two just to be safe. So this is also a good procedure. If one of those beats is yellow, you're not sure why, the timing's a little bit off, you've done the respiration, it doesn't seem like it's the respiration at all. Any sort of questions, ambiguity, my recommendation would be to mid-beat. And then I have a final question here that I can answer, which is the what version of MindWare are you using? So this is the newest version where we actually have the editing statistics. It's the 3.2 version. And so we have, this is one of the brand new features. There's a ton of different things we have, but you know, just sort of undo, redo all. We can actually, if we're on the previous screen, very quickly before we get started, we have functions such as find the next artifact. So that, you know, if clean data before, you have a certain amount of time available to you to edit the data. So that would really rapidly let you know how messy the data are that you have. And here's another really good example that I just noticed in this file, where we have this beat. We're not sure exactly what it is. Why is it being marked as an artifact? Beyond what I've already shown you, I just wanted to highlight that if we do click on this first crosshair here, we can actually left click on what is being presented as an artifact, and we can see potentially why, which of the algorithms it's failing, which, you know, certainly can help us, inform us in the future. In this case, simply there's just been an error presented because we zoom in, we see a peak or ST, the timing actually looks fine. And this is another one of those cases in which we're going to leave that alone. Cool. All right, so I think that's going to go ahead and wrap it up for today. We went a little bit over, but I hope that everyone found this to be extremely helpful. I'm going to go ahead and show you here that we thank you for attending, and hopefully please fill out the survey for us so that we can make these better. And then again, we're hopeful that you can attend the impedance and blood pressure one that we have planned on April 1st. And we're going to continue to support you in that way, and hope to have you all back soon. Thanks to you for attending, and have a great day.